Alright guys, so if you remember correctly, in part 1 of 3.7, implicit differentiation, we defined first and foremost what implicit differentiation was, and when we used it. And I think the easiest way to define it was when to explain when we use it. Well, honestly, the easiest way to go about it is when we have a function that involves both x's and y's mixed into the function itself. Because when there's more than one y, it's kind of, you're almost questioning to yourself, all right, well, which tangent line am I actually going to be finding the slope of by finding the derivative? And so we can notice processes with implicit differentiation with the example that we used the other day. And our example that we looked at the other day was of x cubed plus y cubed minus 9xy equals 0. And we saw y and the x's both kind of together on one side of the equal sign. And what that ended up showing is that it was going to be for a single value of x, it could possibly hit the graph at more than one spot for our y value. And so once again, the question was, well, which tangent line am I going to be finding at the specific point of x naught? And overall, so what I kind of did for us is put together a very simple four-step process as to how to implicitly differentiate and kind of sum up the process for us. So the goal number one was to differentiate both sides with respect to x. So remember guys, when you take the derivative of x, you don't have to keep dy dx. But when you take the derivative of y, since it's with respect to x, you have to keep dy dx, and then eventually you will group the terms together involving dy dx, and then we'll factor out dy dx and finally solving for it in the end. Okay? So let's go right into more of an application-based question. Okay? So what we're going to look into is the question of the following. It says, show that the slope dy dx is defined at every point on the graph of 2y equals x squared plus sine of y. So really what we need to make sure, obviously, is that, when we find what the slope of the tangent line is by implicitly differentiating, we got to make sure there's no problems. We got to make sure there's no negatives inside of a square root. We got to make sure that all of the domain for, in this case, sine or cosine, match up accordingly. Are there going to be any zeros in the denominator? That's really what they're asking us to find here, and to see if, in fact, every single point on the slope dy dx will be defined. So let's just first and foremost find out what the slope of the tangent line is, at whatever random point they're asking us for, by finding the derivative or implicitly differentiating. And we know we're going to have to because we see 2y on the left and a y and sine y on the right. Okay? So let's go ahead and just do what we've been doing in process number one. So process number one, or step number one of the process, tells us to differentiate on both sides. So in order to do so, we'll differentiate 2y. Well, the derivative of 2y is literally just going to be 2, but because we're implicitly differentiating, we keep 2 times dy dx. And then on the right-hand side, the derivative of x squared is just 2x. I don't have to put the dy dx because that's already with respect to x, okay? When you're taking the derivative of with only a y in it, you kind of have to incorporate the x in there because it's with respect to x. And then we need the derivative of sine of y. Well, the derivative of sine we know is cosine of y, but in this case, once again, you have to keep your dy dx. And now our goal is to kind of group everything together that involves dy dx. So I'm going to get dy dx parentheses times 2, and then if I subtracted a cosine y of dy dx over, I have times cosine of y equals 2x. And so that's where we're at right now, and the last step is just to solve for the dy dx. So I'll divide through by 2 minus cosine of y, and we get in the end that dy dx will equal 2x over 2 minus cosine of y. And so, I mean, the real question comes in is where will this be undefined? Well, obviously, we can kind of see where the only problem is going to be is that if 2 minus 2 ever happens. So really what our question is when will cosine of y equal 2? That's the question, and that's the problem. Well, I mean, think about it for a sec. Cosine of y equaling 2, when on the unit circle can we ever have cosine of y equaling 2? In fact, looking at the kind of thinking about the unit circle and what the the domain and the range of cosine gives us, we actually know that cosine of y is never going to be greater than 1. And so, since cosine of y will never be greater than 1, cosine of y will never equal 2. And so, if that's the case, you can substitute any value in for the cosine of y, or for a value of y, and you're going to be inside of the defined portion of our slope in this case. And so we're going to find that every single point will in fact be defined. Okay. So there's a kind of an example there of our first one that we're going to be looking into for today. I want to dive into a couple other ones as well. In looking at, once again, some more kind of application. How can we kind of use the concepts that we've been dealing with in terms of application itself? Alright, so once again we're going back into what we've been talking about in the past about finding the tangent and normal line, where the tangent line is just the line that is using the slope of our derivative at the particular points that they give us. And then remember, we talked about the normal line. The normal line was what was perpendicular at that particular point. And so you want to find both where that slope is, what the equation of the line really looks like at negative 1, 2, and then where's the perpendicular line going to be from the normal line at negative 1, 2 as well. So let's start some things on off because we see two y's in there. That's usually our go-to use implicit differentiation. That's the goal of this lesson. It's to use implicit differentiation. So we're going to implicit differentially on both sides. So let's take a look here. So first and foremost, each of those terms have to be implicitly differentiated. So x squared becomes 2x once I take that derivative. And then we look at negative xy, or minus xy in this case. So you got to think about it. Remember, that's the product rule, right? So really, that is just the derivative of x multiplied by the original y. So derivative of x multiplied your original y, and then the opposite. And then it's going to be the derivative of y times the original part, which is x. And so doing so, we're going to see this is going to be minus, well, when we do x is going to stay by itself, and then the derivative of y is just 1. But remember, because we are implicitly differentiating, you have to keep dy dx. So this is really 1 times dy dx, and then my x value, and then my x is the same, just kind of stayed the same from what they gave us, all right? And then we go ahead and we take the second portion of things, and then we add the original y times the denominator, or not the denominator, but the derivative of x, okay? And so in this case, because it was negative, I'm just going to basically distribute that negative into both of them. So we have negative y times the derivative of x. The derivative of x in this case is just going to be 1. And then to finish it on off, the last part is going to be plus 2y dy dx. Once again, because I take the derivative with a y in it, and it's with respect to x, I need to keep the dy dx in there. And then we wrap things up on the right-hand side. The derivative of 7 is just going to be 0. And so now, we just want to get dy dx on one side together. So we have negative x dy dx plus 2y dy dx is equal to negative 2x, and then I'm adding the y over as well, so I subtracted 2x, added y on over, and I get dy dx is multiplied by negative x plus 2y equals negative 2x plus y here. And then finally, our end result is going to show that dy dx, after we divide through, will be at negative 2x plus y over negative x plus 2y here. So that's what dy dx actually is. And then it says, hey, well, we'll take into account the specific points at negative 1, 2. So we just going to take wherever x is, substitute negative 1. Wherever y is, substitute our negative or our positive 2. So dy dx at negative 1, positive 2 becomes negative 2 times a negative 1 plus 2. And then on the denominator, it was a negative times negative 1 plus 2 times 2 in this case. And so when we kind of combine everything together, you're going to see that we equal 4 over 5. All right, and so that actually gives us the slope of the tangent line at the particular point, negative 1, 2. Remember what the goal was. The goal was to find the equation of the tangent line. So we take that one step further, and we use our point-slope form. So point-slope, in this example, y minus the y1, which was 2, alright, is equal to our slope of 4 over 5 times x minus that negative 1. And when this is all said and done and it comes together, we get y equals 4 over 5x plus a 14 over 5. So there is our tangent line. Alright, so there's the equation for our tangent line. Well, if you want to, remember, it said one step further, and it wanted to find the actual equation for the normal line. Remember, the normal line really is just the opposite reciprocal because we want it to be perpendicular to it. So we use the exact same point, negative 1 comma 2, and just make the opposite reciprocal slope. And so to wrap some things up here, we get for our normal line, y minus 2 is negative 5 over 4 times x minus that negative 1. And in the end, we get y equals negative 5 over 4x plus 3 over 4 for the normal line. Alright, so there's the two things that we were looking for in this particular example. We're going to wrap up with one final video talking about higher order derivatives using implicit differentiation. And as we kind of wrap some things on up here for today, I have a couple examples I want you guys to give a shot on your own. Alright guys, so our example to kind of check for understanding here, if you want to find the tangent and normal lines, the equations at x squared, y squared equals 9 at the through point at negative 1, 3. And we will look into that first thing tomorrow. Have a good one.